Hey guys, so today I'm going to be solving Advent of Code 2024 Day 1. So this beginning part is kind of just like preliminary information, not really important. Let's get to the meat of the issue. So, throughout the chief's office, the historically significant locations are listed not by name, but by a unique number called location ID. To make sure they don't miss anything, the historians split into two groups, each searching the office and trying to create their own list of location IDs. There's just one problem. By holding the two lists up side by side, it quickly becomes clear that the lists aren't very similar. Maybe we can help the historians reconcile their lists. So for example, we have two lists, left list and a right list. Maybe the lists are only off by a small amount. To find out, pair up the numbers and measure how far they are. So pair up the smallest number in the left list with the smallest number in the right list, and then the second smallest left number with the second smallest right number, and so on. Within each pair, figure out how far apart the two numbers are. You'll need to add up all of those distances. For example, if you pair up 3 from the left and 7 from the right, the distance apart is 4. If you pair up a 9 with a 3, the distance apart is 6. So in this example list, the pairs and distances would be as follows. So the smallest number in the left list is 1, which is right here. And the smallest number in the right list is 3, which is right here. And there are duplicates, but I'm sure they get the first occurrence. So the distance between this 1 and 3 would be 2. And then next, the second smallest number in the left list would be 2. And then the second smallest number in the right list would be 3 again. And then the distance would be 1. So you would keep doing that. Third smallest number in both lists is 3. So the distance between them, 3, and the last 3 here would be 0. And to find the total distance between the left list and the right list, add up the distances between all of the pairs you found. And in an example, it would be 2 plus 1 plus 0 plus 1 plus 2 plus 5, giving a total distance of 11. So, your actual left and right lists contain many location IDs. What is the total distance between your list? And as you can see, I've already solved this previously. So, let's go ahead and look at the input. So this is how our input looks like. Here we have these large numbers, and it goes quite far down. So how would we visualize it? How would we go about solving this problem? So here we would have two lists, our left list and our right list. So first off, we would start with our left list, go all the way down until we found our smallest element, grab that, then go to our right list, keep going until we find our smallest element, which is 3. Find the difference. That would be 3 minus 1. The absolute value would be 2. You could do 1 minus 3. Either way, you're finding the absolute difference. Next, you would cross them out of our list since we're done with them. And then on the next iteration, we would start on our left list again, keep going until we find our second smallest, which is 2. Go to our right list, keep scrolling until we find our second smallest on the right side, which is 3. So we would find our absolute difference, which would be 3 minus 2, which would be 1. And you would basically keep doing that. Alright, so now that we have all our differences, we will go ahead and add them all up. So that'll be 2 plus 1 plus 0 plus 1 again plus our 2. And then finally plus our 5. And that will give us 2 plus 1, 3, plus 1, 4, plus 2, 6, plus 5, 11. So that's how we would solve this problem. However, this algorithm is very inefficient. In fact, the time complexity would be O of n factorial. And there's a much better way to solve this problem. We would have to use a new data structure called a min heap. So what is a min heap? Well, a min heap is a type of tree, but the most important property of the tree is that at any given point in time, the tree will have the smallest element as the root node. So it'll always maintain the smallest element at the root. This is good because we can always find the smallest element in O of one time. Constant, right? It's just a lookup of the root. And then after you would remove this element from the heap will have to push the second smallest element to the root now. And that time complexity is O of n, it's O of log n, right? So that's the only time complexity of these two operations, which makes it very efficient compared to an array. So in our solution, we would maintain a left min heap and also a right min heap. And at the beginning of our algorithm, these heaps will contain 1 for the left side because it's the smallest element on the left side, and 3 on the right side because that's the smallest element on the right side in the first pass. So then what we would do is we would grab the minimum by popping it, grab the minimum on the right side by popping it, subtract them together and find the absolute difference. And then we would keep doing that while any of the heaps, or while you can pick one, while the left heap is not empty. So our algorithm would look something like this. So while our left min heap is not empty, and you could do with right min heap, but it doesn't really matter since they're both the same size, we would pop our left min heap, we would pop our right min heap, we would calculate the absolute difference, and we would add that to our total. And we would keep doing that until the while loop breaks, and then after that we would return our total. This gives us a total time complexity of O of n log n. Alright, here I am, opened up my VS Code, and I will be programming in Swift. Don't ask why. So first of all, we're going to go ahead and import a few libraries. Import foundation, import collections. So collections will contain our min heap. So we would, first of all, we have to define our input file. So I have added my input file here. And let's go ahead and pull data from it. We're going to define our left and right heaps. Next, we're going to define our file path. Now that I've defined these variables, next I'm going to load in my data into my two heaps. So now that I've defined these variables, next I'm going to load in my data into my two heaps. Next, I'll define a variable total, which will keep track of the total differences so far. And then, while my left min heap is not empty, let's first start by popping the minimum from our left min heap, and then pop our right min heap, And then, oops. And then let's calculate the difference. And after we're done, we're going to print out our total. So we'll say the sum of all the differences is total. Alrighty. And now finally, let's go ahead and run our code. So Swift run. And there we go. The sum of all our differences is this number, which coincides with the answer I got before. Alright, so let's get started with part 2. So it says, this time you'll need to figure out exactly how often each number from the left list appears in the right list. Calculate a total similarity score by adding up each number in the left list after multiplying it by the number of times that the number appears in the right list. So in this example, the first number in the left list is 3. We start with 3. It appears in the right list 3 times. So that's, 3, 3, and 3. So you would multiply that, 3 times 3, 9. So the second number in the left list is 3. How many times does it appear? 1 time. So that'll be 4 times 1. So you would keep doing that, and you'd keep adding that up until you're done. And then you would return the total. So what is the similarity score? So how would we go about solving this problem? So a naive solution would be to first start on the left side, which would be 3. Next, you would go in the right array and then maintain a count variable. You would initialize it as 0, and then you would loop through the right array, check if each element is equal to the 3. So for example, 4 is not 3, 3 is 3, so that's 1. We would keep going down. 5 is not 3. We found 3 again. We'd increment the count. That would be 2. Keep going. 9 is not 3. So no. We now go to 3 again. We found 3 again. So we increment the count as well. So then the count would be 3. So then you would multiply 3 times 3, which is 9. And then you would add that to our total. So we will also maintain the total variable. See, total. And then you would add that. So it would start at 0, and then we would add that 9, right? And then next, you would go to 4. We would go inside our array again. Oh, we found 4. So that's 1 time. Next, go through our 3. Nope. 5, no. 3, no. 9, no. 3, no. We would keep going down to our 2. 4 is not 2. 3 is not 2. 5 is not 2. 3 is not 2. 9 is not 2. 3 is not 2. So this is not the way to go, right? The time complexity would be O of n squared. Because for every single element in the left array, you're going to have to loop through an entire right array to check if it exists, right? To check the total number of occurrences. So that is not performant at all. A more optimal solution would be to maintain a map of all the occurrences of the elements in the right list. So for example, 3 occurs 3 times, right? So our key would be 3, and then the value would be the number of occurrences it appears. Same for 4. 4 appears 1 time in this list. So it would be 4 as the key, and then 1 as the number of occurrences. And the same thing for 5 and 9. And then what you would do is, you would basically start in the left list with the first element, 3, perform a lookup of how many times it occurs in the map, which is pretty much an O of n operation, O of 1 operation, constant time, right? Which would be 3, right? So then you would then multiply 3 times that value you got from the map, which would be 9. And you would add that to your accumulator. Next, you would go to 4, do the lookup, which would be 1. So that would be 4 times 1, which would be equal to 4. And you would do the same thing for 2. 2 wouldn't exist inside this map, so you would return 0. 1 doesn't exist as well, you would return 0 as well. 3, you already know the value 9, so it would be 9 as well, and then for 3 would be 9 as well. So in this case, the time complexity would be a lot better, which would be O of n. Alright, so now to the implementation. We can basically use the same code and we're basically using the same data, but we're going to do a couple things here. So instead of using a heap, we can go back to using arrays. So what we will do is we will define these two left as an array of int, and then our right we would define in the same way. Alright, so that's fine. Loading of all this data is going to be slightly different. Instead of insert, what we will do is we will append. And then now we are going to define our map. So we'll say our map, which is an int key and a value int. And then keep our total. And then instead of a while loop, we will say for element and right, we are going to basically initialize our map here. So I'll go ahead and just copy this. So let's go ahead and initialize our map. So what we're going to do is we're going to say map element default value is 0 if it doesn't exist already, and then we're gonna increment it. So for every element that we see in our right, we add the element as a key if it already exists. The value will be 0, right, if it doesn't exist already, and then we just increment to that value there if you find it again. So that's the initialization step. Next, we're going to say for element and left, say if let count equal to map element. So if our count exists, we're going to say total plus equal to element times count. And then we're going to now sum all our differences together and print that out. So let's go ahead and run our code. And there we go. The sum of all our differences is this large number. And now finally, let's go ahead and input this in our answer box. And there we go. That's the answer. We have completed day 1.